Hi everyone, thank you for attending today. We're just going to wait a couple minutes so that everyone can get settled in. So if you want to grab a coffee and just relax for a few minutes, we'll start in about 3 to 4 minutes. Thank you. My name is Sean Devine, and I'm a technical sales specialist for ITM Instruments. Thank you for joining us today for this webinar via our ITM University. Today's topic is going to be UPS and battery maintenance in partnership with Fluke. We kindly ask during the presentation that you mute your microphone. The presentation is going to last about 40 to 45 minutes, and then after that, we're going to have time for a Q&A. We encourage you to ask your questions at any time. Simply use the chat feature, and we'll get to your questions at the end during the Q&A period. ITM Instruments has been working closely with Fluke for many years. We pride ourselves on being a leading distributor of Fluke, and this is a result of our dedication to offering you product expertise, service, and competitive pricing. So let's get started. Today's webinar is presented by Dave Robley from Fluke. Dave has been with Fluke since 1984, recommending test equipment solutions for customer applications relating to thermal imaging, vibration testing, power quality, electrical measurement safety, and motor drive troubleshooting. Dave has a level 1 certification in both infrared thermography and vibration analysis. Dave also holds a BSE from Marquette University and is currently working as a sales applications manager based in the Chicago area. Thank you, Dave, for joining us today, and if you could please take it away. Thank you.
Sounds good, Sean. Thanks. And again, on behalf of ITM and Fluke, thanks for inviting us in virtually today. As the title slide says, so we're going to be really covering both UPS as well as battery maintenance. So we'll kind of split this into two parts again in the next 40 minutes or so. So in the first part, really, we're going to be focusing more on the UPS system minus batteries. So we'll be looking at commissioning aspects, also maintenance and troubleshooting aspects. And then also some of the tools and technologies, types of measurements that would be useful when either performing commissioning, maintenance, or troubleshooting. So some of the product categories we'll look at are listed there: thermal imaging, power analyzer measurements, and then also more of a troubleshooting aspect, which would be using a tool called the scope meter. Then in the second portion, we'll be focusing more on batteries themselves, technology. There are test standards when it comes to backup or stationary batteries. So we'll be taking a look at those standards, looking at guidelines, and then also focusing more on the tools, testers that can be used to gauge battery health and what defines battery health. So that's our roadmap, again, for about the next 40 minutes or so. So let's start out with the UPS system itself. Again, keep in mind it's for commissioning, maintenance, and troubleshooting. So that's a typical block diagram of a UPS system where you have your normal power source coming in, providing power to a charger, which can charge the stationary batteries for backup. And then you have an inverter on the output side of that to convert back to AC, which would go through static and manual bypass switch or some other bypass power source if need be, such as a standby generator, all there to power your critical loads. So wide variety of industries, data centers, hospitals, airports, utilities, oil and gas, manufacturing facilities have backup power systems for their emergency systems, alarms, controls, in order to be able to react to any type of issue and then initiate an orderly shutdown and cause no impact in the facility. We're going to start with taking a brief look at thermal imaging, and I'm sure a lot of you are very familiar with or have some degree of familiarity with infrared cameras, also known as thermal imagers. I use the terms there interchangeably, but essentially these tools allow us to see images based on heat, that heat being infrared energy that's being emitted. One of the ways I like to look at thermal imaging when it comes to UPS systems is really more as a screening tool to be able to highlight potential problems that could cause issues, manifest different types of symptoms. So it's an excellent screening tool. Infrared cameras are fast, they're non-invasive, and you can see a potential problem, and then based on what the image is telling you, then you can take action. So there's a lot of different areas in a UPS system that you could check. I'm sure it's not an exhaustive list, but anywhere from the electrical panels to breakers, looking at switches, PDUs or power distribution units, batteries, battery connections, even printed circuit boards, transformers, really anything, any component that might be critical to the operation of that UPS system. I have a few sample thermal images here, and again, I'm sure that many of you have seen examples of that, but there's a few examples that we show here. Namely, what you're looking for are evidence of potential problems. This might be an example of a loose connection where you see a hot spot and then moving on the conductor up away from that hot spot, it appears to get cooler. That pattern is very symptomatic of a loose connection or a corroded connection. You can see overheated components on printed circuit boards, apparent overloading. If this were a balanced three-phase scenario, this looks like this C phase or L3 looks much hotter than the other two phases. So that could be example of an overload or some load condition. But at the very least, it's pointing out something that needs attention, as are all these images. So again, keep in mind, use thermal imaging. If you have a camera on site, UPS systems are a great way to be able to screen for potential problems and rule out potential problems on an ongoing basis. Here's a diagram of a typical contingency supply system at critical installations. So what we're going to be looking at or examining is how by using a power analyzer, you can actually perform proper commissioning, maintenance on an ongoing basis, or troubleshooting, whatever that period is, monthly, quarterly, kind of depending on the scenario after commissioning. So the types of tests and measurements we're going to be looking at, really, they're divided into two stages. One would be pre-installation, so testing prior to connecting your critical loads. What we would be using in the to simulate the load here would be load banks, either resistive or a combination of resistive and inductive, or resistive and capacitive to simulate different types of power factor that might be representative of the loads. So for pre-installation, keep in mind that we're using load banks. And then after the installation, commissioning on an ongoing basis, and actually before you're done commissioning, you would do what's called a combined test. That's where you would actually not use load banks, but connect your critical loads. So these are the tests we're going to be looking at. There's a number of different tests. All would involve use of a power analyzer. So initially, the first test literally is just a UPS functional alarms test, looking for proper display values, making sure that you don't have any alarm messages. The tests after this, the next, I believe there's 8 different tests. We'll be using a power analyzer. Here's an example of a new power analyzer that we have called the Fluke 1777. So I'll be referring to this. It's a full 3-phase power analyzer that can capture all the types of measurements that we're going to be discussing. So test number 2, it's called a UPS specification test. What the analyzer would be doing, and actually for this test, you would actually need to have 2 analyzers, one on the input side and one on the output side, and then to be able to compare readings. So what you'd be doing would be recording voltages, all 3 phases of voltage, current, real power or kW, apparent power, kVA, power factor, and then also looking at voltage and current distortion on both the input and the output. So the process for doing this essentially is first using balanced loads. Again, we're using a load bank here. So first you would use balanced loads, run the test, vary the loads from 0 to 100%, 25% steps, and then record the data. And then also using unbalanced loads. There is a process for doing that. So there will be 4 combinations that you would initiate using your load bank. So the first one on A phase and B phase, or L1 and L2 I'll use, you would have 100% load, then 0 on L3. The second step would be 0% load on L1 and L2, and then 100% load on L3. The third step would be 100% load on L1, 50% load on L2, 100% load on L3. And then for the fourth and final step, 50% load on L1. L2 would have 100% load and then 50%. In that way, you're fully exercising the specification based on both balanced and unbalanced loads. Next step would be a burn-in test. So load the UPS to full rated load, again, via load bank, and then operate from 8 to 24 hours. And what you're looking at, again, is to show that it performs as per spec. This would be maybe an example of what you might see on a power analyzer over time. What you would need in the power analyzer essentially would be that capability to not just measure, but record that data over time, and to be able to save that and then generate upon request a test report. So this is the two images to the right are good examples of that burn-in test recording or a trend over time. Our next test number 4, is called a step load and bypass transient tests. So essentially what you're going to be doing here is really showing what's the transient response, of the UPS as you hit it with step loads. So you'll be going to in 25% steps, you'll be going from 0 to 100 and back, 0 to 50 and back, 50 to 100 and back to 50. And then really observing that transient response. So is it responding properly? So the power analyzer needs to be able to, as is evidenced by the waveforms over here on the right, you need to be able to observe and watch for that transient response even as full load current is applied. And as you can see in the example over here for the 3 phases in question, the voltage waveforms hardly vary at all, even based with a big step increase in current. So that's really what you're looking for. So you need to be able to capture things down to much faster than a single line cycle to look for that transient response. Our next test is a UPS start and stop test. And really what you're looking for is correct operation, when the UPS is switched on and off with full load. And you'll do this at both 50% as well as 100% load. So the process is, while recording or looking for transients, you would, with a power analyzer, again, you would be looking at load voltage, load current, and then the mains 2 and mains 1 currents. Next test is a UPS loss and return of mains test. So what you want to do is, again, using your load bank, demonstrate correct operation for operating at full load off the UPS to simulate a 15-minute power failure. So there you would use a separate type of a tool, or maybe battery monitoring system, to look at the battery cells before and after that 15 minutes of runtime. Our next test will be a UPS loss and return of battery test. So you would run, again, with our load bank, run the UPS module at normal load, and then switch the UPS main input on and off. Again, what you're looking for there is transients, evidence of transients, and then also be looking for load voltage, load current, and mains 1 current. Our last 2 tests, number 8 and 9, are both a load transfer test and then a transfer over to bypass and back test. And again, initially upon commissioning, you're doing all this really kind of as a pre-installation or prior to connecting your critical loads and using load banks to perform the tests. And here we have some examples. So you would run the module at normal load, switch the UPS main battery breaker on and off, and then again, record the same types of things, record transients on all 3 phases, and then look at load voltage, load current, and mains 1 current for proper operation. Last test is transferring to bypass and back. So what you would do is run at normal load, switch the UPS off and on until the load is on static bypass. And then again, capture the same types of events, load voltage, current, and bypass current. And then you would also, when you go off of static bypass to go back to UPS, then you would repeat the same test. So essentially, that's our pre-installation tests. For combined testing, what you would do at this point then is remove your load banks, connect your critical loads, and as well as the standby generator system, and repeat the same tests at 0% and 100% load conditions. So we would want to be looking for transfer between the main supply, UPS, and standby generator to ensure that transients and waveform distortion would stay within acceptable limits. Then on an ongoing basis, periodically, could be monthly, quarterly, you would want to conduct maintenance tests throughout the life of your overall contingency supply system. So you'd follow the combined test procedure for really everything except the standby generator. Generally, recommendations are it only needs to be tested once per year. We're going to focus a little bit more on some of the same types of measurements, but maybe rather than using a full three-phase analyzer, which you could use, we also have troubleshooting tools, portable tools such as a scope meter, which is a combination of a scope for oscilloscope as well as meter for meter readings. And it's a great portable tool, anywhere from either 2 or 4 inputs, variety of bandwidths. So we have a 500 megahertz product, high bandwidth to be able to capture very short rise time events, namely the Fluke 109504 4-channel scope meter. So this can be used to not just measure our AC characteristics, but it can go a little bit deeper into components, circuitry, as is needed, maybe based on a symptom or a problem. So it can look at I/O, inputs, outputs, and control boards of the charger, the inverter, static switch. This is a tool that can measure both AC as well as DC, so it's very, very versatile. It can also be used to kind of quick check that static switch transfer from the normal inverter power to bypass power. The SCRs have to transfer that power pretty quickly, typically in less than 4 milliseconds, to ensure critical loads don't drop out. So a scope meter can make a great tool to be able to show that. We have an example of that where we have both a successful switchover on the right side. We see that there is not a dropout. You can observe that, yep, there was a switch over here, but we didn't lose power at all. And here we have an example of a failed switchover. So that would be one method. These devices can be set up to trigger on or look for certain conditions and then capture waveforms. They can also be used in more of a record mode or a flight recorder mode, where you can actually record the entire event over time and then go back and analyze the detail. And of course, they offer storage capabilities to be able to store waveforms. Another mode that the scope meters have is if you know what a successful switchover should look like, as is evidenced on the lower waveform, you can actually set up or capture a known good signal, known good switchover, and then build an envelope, that's what's in the gray, around that for troubleshooting, so that anything that falls outside the envelope could be captured as a failure. And again, the waveforms can then be analyzed and or examined. So again, for troubleshooting, maintenance, scope meters are a very versatile tool in a wide variety of applications, but especially for the critical backup system. So in summary, there's different modes of UPS testing. One certainly would be commissioning, and then ongoing maintenance, and also troubleshooting. And in each category, there are certain tools that are very useful. Some, like the thermal imagers, are useful in all three phases. So in commissioning phase, making sure there's no issues, making sure you have no improper heat or loose connections or hot connections or imbalance or overload conditions. Power analyzers, very useful in that both pre-installation testing with load banks and then combined testing once you connect your critical loads, and then while cutting standby generator in and out. And then on an ongoing basis, thermal inspections, always a great screening tool. Power analyzers can be used on monthly and or quarterly testing, and then also by involving the genset annually. And then also all three types of tools also would be very useful from a troubleshooting standpoint. So I think we're going to move on to focus on the batteries component of our UPS and contingency system. Stationary batteries are everywhere. Backup batteries are found in all industries. These backup power systems are supported with what are called stationary batteries. So this would include UPSs, emergency power systems, DC power, any type of backup battery. And I won't read the industries there. There's so many mission critical facilities that just cannot afford to lose backup power, either from a data standpoint or even from a safety standpoint. So wide variety listed there. So they're everywhere, and as such, it's critical that your backup batteries, when called upon, are ready. So we'll start to look a little bit, just a brief kind of backup battery 101. Essentially a battery, and a lot of us can relate to a battery, maybe our car battery. It'll consist of a number of individual cells, or I've heard them referred to as jars, connected together in series, often referred to as a string. So a lot of the individual cells are a little bit over 2 volts. And then again, they're connected in series to provide a operating voltage suitable for the equipment or the application that's involved. So typically 6 volts, so 12 volt, we're all familiar with that. Actually, if you have 2.2 volts, that's why typically a battery would, if it's good just for a DC voltage level, is about 12.6 volts. But 24 volt, 36 volt, 48 volts for telecom. So these batteries can be connected then in series to provide higher required voltages. A lot of different cell and battery types out there. I think you're familiar with a lot of these. Some are older technology, some are newer technology. Lithium ion, they have a very high energy density, they're lightweight. They're more on the pricey side, but they're used in smaller applications, certainly newer electrical vehicle systems. NiCads, those are the old technology, generally poor life due to memory effects, hazard materials, so they're not really in use anymore. Nickel metal hydride, again, they're pretty much being replaced by lithium ion. Less expensive than lithium ion, but they do have a shorter life. Lead acid, that's the original battery technology. Really, it's the least expensive of all the technologies. They're heavy, they're very physically heavy, but they have a proven long life. They're very flexible and very useful for a wide variety of applications. A couple different types listed. One are called flooded lead acid batteries, or wet cells, essentially. And then what's referred to as a VRLA, or a valve regulated lead acid battery. And there's a couple different types of those that are listed there, the AGM and gel type batteries. So wide variety of batteries that are out there, but all need to be tested to ensure that they're healthy. So let's take a quick look a little bit deeper as the compared to the VRLAs versus the flooded lead acid batteries. The flooded lead acid batteries, they do have a higher energy density, so that would be a positive. They can also operate pretty well with some severe discharge cycles, so they really give you the best overall lifetime. They do require regular maintenance, and also, a number of them, is part of that maintenance really is making sure that they have battery electrolyte. And also, kind of a downside, fumes can be present during charging. Now, the VRLAs, they're sealed. They're the so-called, and I'll use air quotes because I'm on video, maintenance-free batteries. So the two different types there, the AGM type mat, that actually holds the electrolyte. And in gel type batteries, there's a silica that actually acts as acid and silica acting as an electrolyte. The pluses there, no fumes during charging. However, you have to have accurate charging current to maintain or get the best possible life out of that type of battery. You'll run into both types out in battery backup systems. Here's why I had said that maintenance-free batteries, and used air quotes. Here are the real quotes. They require maintenance. So maintenance-free batteries really are not maintenance-free. No, you don't have to add electrolyte to them, but they need to be tested periodically because they can deteriorate over time in a couple different failure modes. And there's some visuals there, namely corrosion, shorts, process called sulfation, seal failures, and actually due to careless maintenance, you could actually have catastrophic failures. And there's a couple of pictures that show that. So it's essential that really people try to do what they can to make sure that, again, when they're called on, when these backup systems and batteries are called on, that they are ready to work. One of the main causes of failure in terms of battery is relates to heat. You can have conditions called thermal runaway, loose connections, loose intercell connections. It could be improper charging, both over and under over time. Also, what can affect or cause battery failure is having excess ripple voltage on your charging system. So if you have a bad diode, for example, on your inverter, that could actually cause excess ripple voltage, which could actually cause or impact battery health. As we mentioned, if you have a battery and you have a string of batteries all connected together, what happens? If it's a single cell or a single jar goes open, the entire string goes offline. So again, it can have a huge impact. And one bad battery will affect the usable life of the rest of the string. So it'll raise the charge voltage and shorten the life on all the batteries that are in the string. And if you have a high impedance or internal resistance, the battery could overheat, ignite, or explode, which I think is what happened in one of the other pictures. I'm not going to take a deep dive here in the chart. I know we'll be providing the presentation to you after we're done. But there is an IEEE standard, namely 1188, revision in 2014, that really is recommended practice for maintenance, testing, and replacement of VRLA batteries in stationary applications. So you can see that it at the columns on the top tell you what measurements need to be made, voltage and current, measured at the battery terminals, charger output, charger current, DC float voltage, DC float current, temperature, also ambient temperature, but also temperature at the negative terminal of each cell is recommended to be measured. Internally on the battery, health measurement, which we're going to be exploring more, would be cell internal ohmic or resistance measurement. And then also cell to cell connections. And then also if we have batteries strapped together, we want to measure that strap resistance. And then also, as we just spoke about, very important to make sure that your ripple voltage is not excessive. Otherwise, that'll shorten the life of the battery. Now, for all those measurements, it does indicate a recommended interval. And you can see that not all measurements need to be made on a monthly basis. And then others are quarterly, and then annually you do need to make and record those measurements over time. Going to shift a bit, talk about battery states or battery health. And there's really two terms there that we're going to look at. One is called state of charge, or SOC is the acronym. It's really how much charge or capacity is in the battery. How much energy, when called upon, can the battery be delivered? It's useful to know. However, it is an offline test. It's not a destructive test, but if you perform too many or too often state of charge types of tests, you need to have those batteries offline for one, so they can't be used when you're performing your test. But those tests can actually shorten the life of the battery. Also, after you've performed your state of charge test, the batteries cannot be put back in service for a period of time. So oftentimes for health measurements, kind of much in the analogy of using a thermal imager for screening, state of health measurements, on the other hand, is a test that can be used when the batteries are available for service or are in service. So it's essentially using a health measurement, which we'll explore. It's mainly internal battery resistance to indicate how much energy the battery can deliver from being fully charged compared to the original spec. Again, keep in mind, main cause of battery failure is heat. Much like a motor, main enemy of motors is heat. So for every increase of about 8 degrees C, average battery life is halved, and it causes degradation in the plates and the loss of electrolyte. Also, overcharging is something that needs to be checked, and this relates directly back to the standards as far as the IEEE standard for what measurements to make and how often to make them. All of these start to cause the phenomena of internal cell resistance changes. So that's why for state of health measurements, battery resistance can tell us a lot about what's going on. So really we're going to be looking at battery resistance versus impedance. So really the number that is most indicative of the state of health of a battery is actually the resistance measurement. So that's really the gold standard for checking and determining battery health. So when you look at battery resistance, typically what you would use, you'd use a tool called a battery analyzer to measure these very low internal resistances and to look for trouble spots. There's two ways of making the measurements, which we'll come to in a little bit, but essentially what's very useful here and what's key is to trend the measurements. Because the trend can tell you, or if the trend suddenly takes a kind of a sharp change in slope, that can tell you or signal you that end of life of a battery draws near, and you can take proactive action versus the an out-and-out failure. The internal resistance of batteries will increase. So the trend that we're looking at is an increase in internal resistance. The Fluke battery analyzers, which we'll be looking at in a little bit, we use a technique where we can, in order to make this critical measurement and really only look at that resistive component, we actually use an AC current signal, and we are actually measuring an impedance, but through the measurement technique, we're able to extract just the resistive component, which is, again, that really is the gold standard for being able to determine that state of health of the battery. So it's really just the real resistance. It's a fast measurement technique, so per cell, really it's about 4 seconds. So it shortens test times while ensuring the right measurement and accuracy. Now, in order to do that, we need to make a measurement which is called a 4-wire Kelvin connection. You might not be familiar with that, so we'll take a little bit deeper look as to what that is and why you need a 4-wire measurement. Here's the way that a Kelvin measurement is used. We have, again, a test current is used, and we're measuring and looking at a voltage to be able to calculate resistance. If you look at these leads here and these leads here, there is a resistance associated with those leads. Think of it as test lead resistance. If any of you have ever used a multimeter, you know that there's a couple tenths of an ohm test lead resistance. Battery internal resistance measurements are in the milliohms. So test lead resistance would present a huge error. Actually, it's much, much larger than what it is you're trying to measure. So essentially, a 4-wire measurement allows you to compensate for the test lead resistance and take that out of the equation and take out that voltage drop that would occur because of your test lead resistance. So that's why a 4-wire measurement is required for battery internal resistance. And this is a look at one of the exact actual probes where, you know, one of the probes carries current, the other one senses voltage. Again, we're making a 4-wire measurement. There would also be a black or a negative probe, which would have the same construction. The probe tips there they're replaceable. They're sharp. They bite into the metal that you're trying to get on, so you'll have good contact. And it's important that they're replaceable. That's probably a consumable item for people that are doing a lot of battery testing. And as pictured there below, we have a variety of probes, different probe lengths, and also angled probes, all with these tips to be able to access difficult measurement locations. Now we'll take a look at the battery analyzers themselves. The Fluke, the BT521 battery analyzer, that's our most complete kit. Again, all designed, and it has the replaceable Kelvin probes for the 4-wire measurements. The tool has something called the battery sequence mode, which we'll look at further. It makes it very easy, straightforward to the operators to walk through the testing process, make their measurements, automatically capture the measurements, and then save them in the tool for automatic report generation. So it saves a lot of time. You don't need to write anything down as you're walking around performing your routine measurements. The tester is also really an all-in-one. So we talked a lot about battery resistance, that health measurement, state of health in milliohms. It, of course, makes that measurement, but it also captures DC voltage. And for certain applications, maybe in switchgear, there might be up in the hundreds of volts. Well, this tool can actually measure up to 1,000 volts DC, and for three-phase UPS battery systems, you're working with perhaps 480 volt versions, so you don't have to have that separate multimeter. This has all the appropriate CAT ratings for transients and able to make all the AC and DC measurements that you need to make. If you recall, we said that recommendations for a temperature on the negative battery terminal is useful to look at over time. This actually has a built-in sensor, infrared sensor, that will capture that negative terminal temperature. And for testing the charging systems, AC ripple voltage was a very important measurement to make, as well as current measurements. And all the accessories are included to make all the measurements that you need to make. So let's take a little bit closer look at the sequence mode. This is the main mode of operation that people that perform battery testing would use. So the idea there, the goal is really to have a structured, paperless, repeatable way of going out and very quickly making the right measurements by one person. You don't need another person with you to write things down on a clipboard, to have all the values and to store it internally in the tool. I had mentioned that measurements can be saved automatically. So the tester can actually determine when you've made a good, valid measurement, and it can capture it automatically for you. So all you really need to do is probe and go. However, if you want to make manual measurements and manual saves, you also have that option. You can set up user profiles, so locations, plant or area locations, or if you're in the business of battery testing, a service organization. It can be customer sites, areas in that site. You can have device names, battery strings with X number of batteries in the string. So you can create these profiles either in the tool, or you can create it in the software that's included with the tool. So we had said that trending is very important. The idea is to be able to have these sequences preloaded, pre-programmed in the tool, just make the measurements, save the readings, and then get that information out to the software to be able to look at those trends over time. Up to 100 profiles can be stored inside the tool. Again, we can create the profiles either in the tool itself, or you can create a template in the PC software, load it into the instrument. So all the different attributes there, site names, device names, battery string numbers, you can use any or all these in order to make measurements. And what we'll do on the next slide is we'll actually take a look at, when you're using it, what that might look like. There's a sequence button on the battery tester, and then you have the option to load in the sequence name that you want to use, and then as a user, then it would start to prompt you through, and on the screen you can see what looks like 32 batteries in the string, and it also will tell you what battery number you're testing. So it looks like we've stored something because it's filled in reverse video in battery number 1. And the cursors have moved to battery number 2. So that's the one that we're testing. So you can just place the probes on battery number 2. It could be auto-saved or manually saved, and then it would automatically advance. What's highlighted there is that is the number string, so you can easily see which batteries you've already tested and which ones have yet to be tested. Something that's pretty useful also is, and we'll come to this when it gets a little bit more to the software, but it's handy to know what an average reading is in the string. So the tester can help provide that information after the fact, and we'll come back to this, but again, that's there mainly to be able to, if you don't know yet what good looks like, one of the techniques for doing that is to take the average of all the cells or the batteries in the strings and then use that average value as a baseline. So this automates that process for you. And also, oftentimes, batteries are strapped together. So by pressing the F2 key, you can switch between measuring either the battery resistance or the strap resistance. You just keep pressing F2, and you can switch back and forth between measuring battery, then strap, then battery, then strap. The software is very useful for analysis and trending, and that's really, again, what we're looking at. We've got a couple different images there. One is really showing all the individual cells, and the tester does allow, if you know, either through experience or from measuring new batteries, if you know what a good value should be, you can set that as a limit, which is indicated by the red horizontal line, and individual cell measurements or battery measurements can be compared to that limit. And anything out of the limit, this would be on an individual set of measurements, would be highlighted visually as a fail. Also, another way of using this is that trend, which is so important over time. And that's what our lower graph is showing there, showing on a battery by battery basis that trend of resistance values. And so really what you'd look for there is that more dramatic change in slope, which is very indicative of battery that is experiencing one of the failure modes that we discussed earlier. And of course, in the software, it can help manage, generate those reports. Essentially, you can say what you want included in the report, and then generate that hard copy output, as well as creating profiles and sequences that can be loaded into the tester. So in summary, maintenance-free batteries need maintenance, okay? And the IEEE 1148 standard is the guideline as far as when and what measurements to make. State of health is an online measurement that you can make, so it's less invasive and it can still be very useful for determining health. Doesn't impact battery life, as does state of charge types of measurements. Battery resistance is a key health indicator that can provide insight into one of the various different number of problems that could be occurring. So practice there, establish a baseline, either if you know or measure good batteries, or by getting the average value in strings, that can be useful to have something from which to compare. And then what's really key though is to observe the trend over time. Resistance goes up as a battery loses capacity, so that's what you're looking for. Battery analyzers can be very useful tools to be able to capture all the health measurements, not just the resistance, but ripple voltage, temperature, charging currents, etc., with a single tool, and also enable that automatic testing and automatic record keeping in the tool that can be offloaded via that sequence mode into the included software to trend and analyze. But I think we're to the questions portion. I ran a little long in the presentation, so sorry about that. Thanks for indulging me. And Sean, do we have any questions that have gone into the chat box?
Yeah, perfect, Dave. That was great. I mean, definitely very informative. And so far we have a few questions. So Everyone, it's time to take advantage of having an expert like Dave with us to answer any and all questions you may have. So to send in a question, please use the chat feature. And please note that if there's any product-specific questions, such as pricing or availability, we encourage you to visit our website, itm.com. There you're going to find a list of products, pricing, technical specifications, as well as all our contact info and the different ways you can connect with our technical support staff. So we'll be happy to address any and all questions that you may have. So Dave, first one up is from Nick, and it is, what happens to the maintenance-free battery if you add distilled water to top it up?
Maintenance-free batteries, as far as I'm aware, there really is not a way to be able to, that would be the VRLAs, not a way to add distilled water or an electrolyte. So was that the question, or is that kind of more the on the standard lead acid?
Yeah, Nick, if you want to send a follow-up, might help us clear things up a little bit. In the meantime, Daniel has a question. For the BT521, does the battery have to be fully charged?
It does not. No, it doesn't. It can be used at any time for testing, because really it's more of a, you're testing the, not so much the state of charge, but the state of health, which is that internal resistance, and using that internal battery resistance as the health indicator for trending.
Perfect. Yeah, no, that answers that. Let's see what else we have here. What would be a good battery internal resistance measurement value?
You know, and actually we get this a lot. Typically, you can, although it's difficult to find, on a battery by battery basis, you might be able to, with some research, find what that internal resistance measurement should be from the manufacturer. But from what I've heard from people that perform battery testing, it's difficult to find, and it can also be dependent on the technique that's used to measure the resistance. Some don't just give you resistance, they'll give you a number that includes impedance. So I think what we found is, from a practical standpoint, you're actually better off taking the practical approach a couple different ways. One would be, if your batteries aren't brand new, you have to start from somewhere. So one method has been to, by measuring all the batteries in the string and getting the average impedance, or I'm sorry, resistance of internal resistance across all the batteries and cells in the string, using that average number as a baseline, that has shown to be good if you want to use threshold limits, for example, as is in the one software example there with the bars, the histogram of red and green. Another one certainly is, as you get new batteries in, would be to test them, and to learn what that good value looks like. Again, for setting limits, which you can do in the tester, but even in absence of those numbers, the trend can provide a lot of information, or it's more the change in the trend over time that can tell you a lot about the health or lack thereof of the battery.
Perfect. Yeah, that was a great question, and I think I'm learning from you that it's all about establishing that baseline and the trending. We have another question from Roberto. We'll try to get through these as quick as possible here. If you rule out one battery to be degrading, is it okay to change that particular battery?
Yes. Yes, that is. Now, there might be implications, of course, for your battery backup system while you're doing that, performing that maintenance. But that would be essentially offline then. But yes, that would be the typical path you would take.
Perfect. Gabriel's asking, why is it not recommended to use an automotive type battery load tester?
And can you repeat the question, please?
Yeah, sorry. So Gabriel asked, why is it not recommended to use an automotive type of battery load tester?
Oh, okay. Automotive. Got it. Sorry about that. I'm not that familiar with those, but I believe that they are more of a state of charge tester. But again, yeah, I'm at a little bit of a disadvantage with the automotive ones. Also, they might not give you capability of a variety of battery systems, different voltage levels, different, cell interconnections, strap resistances, things like that. But it's more, my understanding of those is that they're more state of charge testers, by applying a load. Certainly I'm not familiar with the documentation capability of those. As the automotive ones, you're typically testing, single battery installations.
Perfect. And so we really are pushing it to the end, everyone. We'll try to wrap things up quickly, but Kelly has one last question. Testing a string of jars, why do the jars in the middle of the string tend to fail before the ones closer to the beginning and end of the string? Not sure.
I actually haven't heard that before. I'm going to jot that down.
Okay, great.
Somebody, so that's it sounds like that's been their experience. I don't know. I'll follow up on that. Yeah, I've not heard that one before. So I'm not sure why that would be, one more in the middle as opposed to anywhere else. But how about if I look into that one, Sean, and I'll let you know. Then you can pass it along.
Yeah, that's great. Thanks, thanks, Dave. So Kelly, we'll follow up with you on that. Unfortunately, everyone, we see some other questions coming in. We won't have time to answer them right now, but we're going to send you some emails later this afternoon with answers to any other questions you have. So on behalf of ITM University, we thank you all for attending the webinar today, and we hope that you found it informative and helpful. ITM Instruments is available to assist you in any way. Simply visit us at itm.com for anything you need. Through itm.com, you will have access to our entire list of Fluke products with descriptions and specifications. You will also find our contact info in order to contact and connect with one of our technical support staff who are able to answer any and all questions you may have. At the end of the webinar, we do have a very short survey that we'd like you to complete. Your feedback will assist us in improving and allowing us to bring you more topics that are of interest. We have some upcoming webinars in the next few weeks and months, so please visit the training section on itm.com for a full schedule of the upcoming webinars and topics. Lastly, don't forget that as a thank you for attending our webinar today, your name will be entered into a draw to win $100 for your next online order. The winner is going to be announced on our social media channels, so please be sure to check us out there. Dave, can't thank you enough for the informative webinar today. I think we all learned a lot, and you have a great rest of the day.
Thanks, Sean, and thank you, everybody. Thanks for having me on.
Perfect. All right, there will be a copy of the webinar being sent out, everyone, so you'll be able to rewatch this later on. Have a great day, everyone. Take care.
Take care, everybody.